Soares-Furtado. I'm sorry, I don't know exactly how to pronounce that, but I was assured it was close enough. Melinda got her bachelor's degree at Santa Cruz, UC Santa Cruz. Did research with Enrico Ramirez Ruiz, and she went on to a PhD at Princeton, where she worked with Gaspar Bacos. And Melinda has, in addition to tremendous having done a tremendous amount of research, has also done a lot of education and mentoring. So quite unusual for a postdoc to have that level of experience. So she's currently a Hubble Fellow at the University of Wisconsin at Madison. And she's an expert on exoplanets in uncomfortable situations, I guess is what I like to say. So without further ado, Melinda.
Thank you so much for having me. I really love this campus, and I been beaming about the Midwest for the last year or so, and so happy that this is going to be a permanent home. I'm starting a faculty position at UW-Madison in the fall. So those of you that are undergrads looking for grad school opportunities or want to apply for postdocs, happy to talk. So yeah, I'm going to talk. I was invited to come talk about tempo, but I was here not very long ago. I was here in May of 2022, and I talked about tempo. And I was assured that probably some people won't remember, you'll be fine, but I just can't do that. I really want to still talk about tempo and share with you what that survey is. It's using the Roman spacecraft that will be launched forthcoming to look for moons around exoplanets that are free floating. We'll talk about that, but I'm going to talk about it in a broader sense of worlds and suns in context. This is really thinking about the key priorities that, as set by the National Academy of Sciences Decadal Survey, very long-going sort of group effort to define what the major priorities of astronomy will be. And there were three sort of key concepts that were taken away, one of them being worlds and suns in context. This priority, really thinking about pathways to habitable worlds, that is something I'm very interested in. But I'd like to understand the connections between stars, the worlds that orbit them from these earlier times when they have these nascent disks that are filled with dust and gas, but also thinking about them as they're forming and evolving and putting them into the context of their ages and their environments. And the other thing I'm going to argue, if we really want to think about it as being called worlds and suns in context, is that moons too are worlds, and they're actually interesting places to even think about life in our own solar system. Very excited about the Europa Clipper mission and what we might be able to find. So really, I think the title is quite fitting if we're going to talk about moons and young planets and some of the things that we've been working on in my team. Yeah, I love interactive questions, please. So like, feel free to do that, and I have ways that I can like stop early if like we end up getting into a conversation. That's also fine.
This is a technical comment.
Yes.
Sorry about that. Could you share your other screen on the Zoom? They're not able to see your slides.
Oh no.
Those who are joining remotely.
Okay, let's see again. So this is if it's just the keynote, but maybe I just do desktop one, and then now they should see a Slack conversation that hopefully is not too snarky.
All good.
Floating panels, is that fine?
All good.
When you say habitable, do you mean habitable for humans or for any life?
Okay, so I mean life in general. I'm very interested in whether or not life finds a way, if you will. But when I'm thinking about life in sort of a very sort of simple way, it need not be carbon-based. It need not even need a photon. I'm going to talk about in a few slides something called chemosynthesis, which happens on our own Earth, so it's not that unusual. But this idea that heat formed from tides and hydrothermal vents can actually produce the sugars and things that can then form this sort of cyclical nature of life. But I am very interested in whether or not there's sort of universal laws of intelligence and all this. But at the moment, it would just be interesting to see if there's any sort of cooperative life at all, more or less, in our backyard. Okay, so I'm going to talk about the worlds and suns in context. In context one, which we're going to talk about for a while, is going to be this age-dependent environment. That environment matters, and environment changes as a function of age for these worlds. And to really give you a sense of the scale of these changes, I'm going to just sort of give you this comparative example of the sun's size today and the size of the sun when it is on the tip of the red giant branch. We're talking about incredible changes in size, changes in density, changes in luminosity, the habitable zone moves, and with those effects, the planets that surround them are definitely impacted. In fact, sometimes planets are swallowed in the process, which is very much going to be the conclusion for our inner rocky bodies, Mercury and Venus most definitely, and depending on these sort of dynamical interactions, perhaps even the Earth. And so if we combine the known exoplanet population, thinking about it back in 2021, as put together at that point in time, and we take, the sum of now more than 5,000 exoplanets and think about their relative orbital separations to their host stars, in one animation, colors are meant to give you a sense of the differences in those stellar properties. But the thing you should take away that for all of the planets that we have discovered at this point and characterized, the vast majority of them orbit stars not that different than our sun, not that different in terms of their mass, not that different in terms of their evolutionary state. And so if I was just to expand this object over time and think about how the size of that sun-like star will change, we really are biased right now towards objects that are pretty closely orbiting their host star and are going to suffer this eventual fate. And this is likely due to, it's definitely due to the observational biases inherent in the transit and radial velocity method, that we want things that really do change that center of mass of their star. We want things that are going to block a substantial amount of the stellar light. And so there is that bias. But even if we account for the occurrence rates of these planets and stars, and we think more broadly about these biases, the fact of the matter is that a third of all sun-like stars have planets larger than Earth with orbital periods about less than a year. And so what that means is that on their sort of evolution to the red giant tip, these objects are swallowed nonetheless. It just may be at later stages of that evolutionary sequence. And so this is not an uncommon phenomena. It's not a very long-lived phenomena either, the transient process. But we know, this is from some work that I did with Morgan McLeod and Matteo Cantiello in 2018, that there's a significant amount of kinetic energy that's being lost. If you just think about the orbital decay energy that's being lost in this process, and we look at this on what's known as an HR diagram, effective temperature versus luminosity here, and we plot different stellar tracks, and we think about at any point, if you were to ingest a planet, at the orbital separation of that star's size, what that ratio of the star's intrinsic luminosity, how much energy is putting out, to how much energy is going to be supplied to that star, it's 10 to the 4, 10,000 times more if you're basically swallowing your planets at early stages near that main sequence turnoff. Where that energy goes, we don't know. There's going to be some added slides here where we can start to think about where it's going, but it is being liberated and it's substantial. It's particularly substantial if that swallowing of your planets is happening early on. So not only is it not a negligible phenomena, it's not really a negligible energy transfer that's going on. Yeah.
We have a question from Brian.
Sure.
Hi, Melinda. So you may be going to talk about this, but the getting to the tip of the red giant branch, that phase doesn't last forever. Is there any chance a planet could survive that?
Maybe Brian, you can say more. It's true that it doesn't last forever, and in my mind right away goes into like occurrence rates and the likelihood of finding it. But how are you making the next connection?
Well, I'm just wondering, so it'll be unpleasant for the planet, but I don't know exactly how dense the atmosphere will be where the planet is and the dynamical friction and all of that. So the drag rather, but is it for sure that the planet is eaten before the sun recedes?
If you would have asked me if you would have asked me 4 months ago, I would have given you some simulated data on the gravitational binding energy compared to the virial temperature and the ram pressure. And I would have said, mostly, if you're a gas giant, you're going to be destroyed in the convective zone. But if you're more dense than this, you can survive. However, you're not going to see what I'm doing. I'm drawing on a board. If we think about this planet's cross section, think about even like a rocky body or a gas Jupiter, gas giant. There's a certain amount of pressure that's coming from the top. We call it the overburdened pressure that's actually keeping this object compact. So there is some self-gravity that's going on, but that core, I'm coming to appreciate more and more, does not want to remain bound. There's a lot of energy locked up into this core, and you actually only need to dissociate enough of the overburdened pressure so that the expansion that naturally wants to happen just because of the energy that's locked up into this core can actually sort of lend its aid into the disassociation process. So this means that for our simulations where we see disassociation where we want it, that still holds, but it may even be more optimistic than this, because once you were sort of able to liberate enough of that overburdened pressure, then you have something that's expanding into the envelope or the radiative regime of the star. So I'm becoming a little more optimistic that you can dissociate objects that are maybe more massive gas giants. Now with a brown dwarf, you're now talking about densities that are much larger than the star itself. And whether your brown dwarf starts accreting your star and you create a low mass near like close binary pair, I don't know. And I think there'd be really some interesting work to do there. But certainly for the gas giants, it seems like it's more likely you dissociate everything than we thought. And we're seeing evidence of that in some work that an undergrad is leading right now, where we see not only signs of the material that's being dissociated from a massive 5 Jupiter mass planet, but we're seeing species that are iron loving and would have been in the core in that thin convective region, which goes against what the simulation would have predicted, unless we assume this overburden pressure argument holds. So I think it's a little more nuanced. Sorry, there wasn't like math or anything. I'm just trying to get the visual perspective of this overburden pressure is actually helping to keep this this core together. In fact, if you even think about it further, like Jupiter doesn't even have a core. There's so much energy inside that central part of the planet that it actually permeates throughout the star, and it's more of like a sort of convective body, almost akin to like an early star that was purely convective. Okay, is that okay, Brian?
Yeah, that's super interesting. Thanks.
It is really interesting. I think there's a lot more projects to do. So I was really excited when a colleague, Keisha Lay, who's also a Hubble Fellow at MIT, put this Nature paper out back just this May, where he saw in the WISE data something that was not there in the optical at all, that suddenly appeared in the optical and then appeared bright in the infrared, whose mass ratio was indicative of something like a luminous red novae, these sort of stars converging together, but was actually the mass ratio was inferring a substellar companion. And even the brightness and the peak of these sort of transient signature is indicative of a planet that's actually been consumed. It was a really short-lived event in the optical. You no longer can see it in the optical. It's too faint for us, even when it was showing up in the optical, for any kind of spectroscopy to have been done. But that long sort of infrared decay is still being seen. And it's exciting that these transient events exist. They're just really rare. And so you need sort of a whole WISE field, WISE being this infrared survey, to go and to look for these things. But it does make kind of a splash in the news. So the New York Times picked this up, and they always have their headlines that are a little, it's the end of the world as we know it. Okay, but I guess Planet Engulfment sort of picks up the publicity sort of easily, and they did have this really beautiful animation of the sense of a planet that's being ingested by its host star. And you should point out here too, it's not just that the star is expanding into its planets. You also have this tidal decay that's going on as there's tidal energy, and therefore energy being lost from the system. Lots of accretion that's going on. Yeah.
Is the tidal decay maintained for any like long period of time as it does it disappear after that? I think that answered the question. I will leave it there. Thank you.
Yeah, and it depends too on the time scales of like the stars. The star is more rapidly expanding in size and burning through its reserves the further it is away from the main sequence. So it depends on that initial orbital separation, depends on the eccentricity, how close are you getting and how much are you losing on each pass. So you can have situations where things can only make a few passes. You can have situations where they make many more. You can have situations where they were doing fine and then the star is really taking off now. And so they're all sort of unique. And I work with a really wonderful dynamicist, Alexander Stefan, at the Ohio State University. And he does a lot of work on trying to understand what sort of progenitor could have possibly been here based on what we see. Yeah.
What's the mechanism that causes an increase in luminosity?
Okay, so what's happening is initially the star is luminous because it's burning core hydrogen reserves, right? And so it's basically combining hydrogen into helium. There's a really small amount of energy that's then being converted and lost, but this is happening on a really large scale. Eventually, it's going to run out of that core hydrogen supply, and so it's going to move now to shell hydrogen burning. That's really what's happening as we're moving off of the main sequence turn-off. There's even more complex.
When the star eats the planet, this was about a transient event which was caused a very brief increase in luminosity.
What's causing that transient event? Okay, that's a really great question. Sorry, I thought we were thinking about the expansion.
So with the transient events, this may have more to do with the fact that when you're raining on this material and you're accreting, you are producing some luminosity in that process. But it also could be that the star's puffing up a little bit in the process of the energy being liberated. Could also be that you're changing, I'm seeing in MESA models, you can change the mean molecular weight and the opacity, which then also changes the luminosity and observables of the star. But they don't last forever, these changes, and depending on what mechanism it will change, the signature will be differently lasting. But it could be a combination of these things. I'm not sure which. No. Okay, but since I'm not really going to be as lucky if I'm looking to catch them in the act, I'm glad that people are looking at the transient sky, and with Ruben, we will see many more transients, and please, let's all keep doing that. But we know that engulfment has happened already for many systems. In fact, I'm going to argue as I'm going forward with my career that engulfment is really common for young stars. And so it may be the case that stars are even self-enriching until they form their orbital resonances and they have their sort of stable planetary systems. But an aside, can we see any sort of chemical signatures that would be indicative of a planet that had been swallowed? And one way to think about the sorts of species that may be abundant in planets and not so abundant in stars is to really compare the abundance of a pristine meteorite. This is an undifferentiated calcium chondrite meteorite that you might find in any geology museum. And using that as a proxy to scale up for planetary bodies. It just so happens that when you look at the abundances of a meteorite and a gas giant and a planet, they're not too different. So it's sort of a useful proxy to first order. And then we'll look at the abundance of the sun. And what we'll see is a nice 1-to-1 ratio, which makes sense. They all form from the same common molecular cloud. So you'd expect them to be, predominantly the same. That being said, if you're a noble gas or you're volatile, meaning that you're lost with not a lot of, you're in gaseous form with not a very high of a temperature, you need more mass to actually gravitationally bind you to that object. So these lower mass chondrites are going to have a harder time with having noble gases, and volatiles, they lose them. If you just bulk them up, then they would be able to keep them just the same. But lithium is one of these species that's actually far more abundant in your meteorite and far less abundant in the sun. And I'm happy to talk why that is, but very briefly, it's because lithium is fragile, and stars, when they're converging onto the main sequence and they're purely convective, they're able to burn their lithium reserves pretty steadily because the core temperature of that star exceeds the lithium burning temperature. But meteorites and planets never reach that temperature and therefore are able to keep their initial lithium supply just fine. And once the star is now in its sort of sun-like form where it has that convective shell, the base of that convective zone is not hot enough to destroy the lithium. And so if you add it later on, you can go ahead and see it now in that zone. And so that's why we want to go after lithium as being a useful tracer, but I'm very interested in what other tracers could there possibly be. So a nice toy model question experiment that I wanted to set up was, let's say I basically deposit the entire planet's worth of lithium, knowing how many atoms of lithium and how many atoms of hydrogen a gas giant would supply. Let's say I put it into the convective zone of the star, where it's going to be perfectly mixed, and I'm going to observe it on the surface of the star. What is the statistical significance of that signature? Can I get a sense of what the lithium baseline of the star would be, what the variance of that baseline would be, and can I determine whether or not we're able to get a 5 sigma statistical significance? And to do this, I initially was going to start with all of these MESA models that were going to tell me how much lithium the star had at any given point, but these models were off by about an order of magnitude when I compared them to data. And so instead, I've been leveraging spectral survey data to try to get a sense at any point in a star's life, if you're a 1 solar mass star and you're on that main sequence turnoff, how is your lithium abundance changing? What bin am I in, and what's the variance in that bin? And I did that for a whole swath of stars between 1 and 2 solar masses. And then I could post-process, add in that lithium supply and ask myself, how statistically significant is that lithium now, knowing what the variance is, what the baseline is. And what I saw was that there was a huge swath of the HR diagram that really ruled out 5 sigma statistical significance. The lithium you're adding is just too dilute, or the variance is too high. And so you're not going to be able to say this lithium is definitively, sticking out in a statistical way. However, we noticed that there was a region between, sorry, let me just explain this figure for a second. At any point in this figure, what I'm doing, this very dot that's being plotted, is I'm basically looking at the internal structure in MESA, how much mass is in the convective envelope, the temperature at the base of that envelope, so how long does that lithium stick around in there? And then I'm post-process adding in a gas giant's worth of lithium. And I'm saying, based upon the baseline here and the variance, how statistically significant? And the answer is not very if you're a sun-like star. And then we do the same argument a little bit later, where now there's more mass in the convective envelope, it's gonna be even a little more dilute, which is why this color is getting darker. Again, let's go ahead and add it in, and let's see whether or not we get statistically significant abundances. And what we found is you really need to be between 1.4 to 1.6 solar masses. You didn't even have a convective envelope on the main sequence, you're just sort of forming it now that you're evolving, you had a radiative envelope. So it's not very mass rich, you're not gonna so dilute your signature. And we predicted you should see a pileup of lithium enriched evolved stars if you go look for them. And sure enough, a year later, that pileup was observed in the Lamas data set, which was a really affirming great thing. What we saw was that the enriched giants in the Lamas data set tended to be preferentially between 1.4 to 1.6 solar masses. And this makes sense because if you're eating planets, you're more likely to be able to see them there. It's not that engulfment's more prevalent, it's just that you're biased towards being able to observe them. And so that pileup should exist, and it's been seen now in yet another survey. Okay, so lithium is great, but stars can actually self-enrich in lithium. I'm not gonna go into this because we don't have time, but there's ways that stars can actually decay beryllium into lithium. And how do you know all of your lithium is coming from a planet? If you don't know all your lithium is coming from a planet, it's gonna be very hard to back out how much mass that star swallowed. So what I would really love to know is, are there other tracers? And how are the chemical properties of a star that we think has eaten a planet different from one that hasn't? And what can we learn about the ingested companion? Can we learn about the bulk composition? Can we learn about the mass of the system that was eaten? And so there's an undergraduate named Brooke Cotton who's working on an honors thesis and was part of the Lamont RU program, which I was mentoring, that's been doing just this. We've actually found a really interesting star. It's shown here on this beautiful color magnitude diagram, which you're seeing visually what these different spectral types would look like to the eye for an O5V star, for example. I love beautiful plots. So here we're just seeing, again, another color magnitude diagram. We're getting a sense of what the age of this system is, what the mass of the system is by comparing it to stellar tracks. And what we find is that this is more massive than the sun, but slightly evolved star that we have found. And what's interesting about this star is that it has a really highly eccentric brown dwarf companion that's close by. It's indicative of some kind of dynamical scattering event. It's also super enriched in lithium with a 5 sigma statistical signature. And so what Brooke has been doing is curating a sample of stars that have similar locations on the color magnitude diagram, similar spectral energy distributions, so we can infer similar things about their effective temperatures, their surface gravities, also similar iron abundances. And we can go 10 angstroms at a time by co-adding high precision radial velocity data. And we can see, in addition to the lithium being more preferentially enriched for our target, if we have a much larger control sample than this now, where else do we see differences? These are two controls that are chosen to be slightly more iron poor and slightly more iron rich. So really this black line should be squeezed between the blue and the red throughout. But there are specific places, lithium being one of them, where that's no longer true. And we would like to figure out how statistically significant those signatures are. And is there an ensemble of tracers? And that is what we're finding. We are finding an ensemble of tracers, and we're working with planetary scientists to try to understand how deep should those tracers exist in the planet, therefore how efficiently disassociated was the object that we think was ingested. This is part of this Goldschmidt classification, this idea that different species in a planetary body like to be locked up in different depths. So if you're an atmophile, like one of these noble gases, you prefer to exist in the atmosphere. If you're a lithophile, you prefer to be locked up with an oxygen-like species, you might exist here. If you're a chalcophile, you really like to be around sulfides, then you're going to be in a slightly deeper troposphere. And then if you're a sidereophile, you prefer to be an iron-loving element, you tend to seep down toward the core. And so if we can see species that sort of range across these different depths, then we can get a sense of how efficiently disassociated our planet might have been. So this is what we're working on now, and we hope to submit this to Nature by the end of the semester, but we'll see. Okay. So I talked a little bit about the environment's matter. Also, the ages of systems very much matter, and I'm really keen to work with students right now to try to find Earth-sized planets that are nearby and young. And this is actually quite hard to do because it's hard to age date stars. How do you know how old your star is if it's not in a group or there's not some real strong markers? So this is a triple planetary system. The first two were found about 2 years ago, and this latest planet is an Earth-sized planet, HD 63433d. This was found in the test data set and was co-led by myself and a graduate student. And what's wonderful is it's actually found in a co-moving group known as Ursa Major. Ursa Major is this co-moving group that we're in the middle of. Its stars are only about 20 parsecs away. And really at any line of sight, whether you're in the northern hemisphere or the southern hemisphere, you can find members. Some of those members happen to have lithium measurements. We can do a lithium versus color sequence, and we can see that clusters of different ages, if you're 670 million years old like Precipice, then you have this steeper slope, versus if you're quite a bit younger like the Pleiades, you haven't really efficiently burned all your lithium yet, so your slope is not quite as steep. And we can see that the Ursa Major system is largely tucked between the two, except for what's known as a lithium dip that I don't have time to go into why that exists. Similarly, we can also look at the rotational profile or the gyrochronological sequence, and we can see as a function of color that there's this rotation period color sequence where our younger systems tend to be more scattered. There's lots of arguments about why you see the scatter and they haven't yet converged, and we talked about this a little bit, I think, during the lunch. So I'm happy to come back to that offline. But as these clusters get older, they start to converge onto the main sequence. The lower mass stars or the redder stars are the most reluctant because they have a harder time shedding their angular momentum. But what is happening is they're converging onto the sequence, and yet again, the slope is indicative of age. And we see that our star, which is literally a star here, fits nicely with this group. And this means we can age date it, and that it's young. It's 10 times younger than the sun, 400 million years old. It's one of the youngest Earth-sized planet around a sun-like star. And it's actually also quite close. Oh, I meant to grab the other one. Sorry, this is supposed to be distance on the right-hand side. It's also quite close in proximity, so it's only 20 parsecs away. And this is a paper that we just submitted, and we're very excited about the possibility of following up on this system because these 3 planets are transiting their host star. And so it might be interesting to know whether or not there's any kind of atmosphere around this young Earth-sized planet transiting a sun-like star, and whether 400 million years is enough time to completely disassociate or photoevaporate that material. So this is something that we very much would like to do. In addition, I'd like to look at the Ursa Major system much more. So something I'm hoping to do with graduate students and undergrads is to get SALT data, which we've already proposed for, to look at all the targets in the southern hemisphere that are bright enough to be looked at. This is going down to 0.2 solar mass and dwarfs, all the way to several solar mass, more evolved stars. We see our target there in red. Because they're so nearby, we also can get a white dwarf sequence, which means we can age date the cluster based upon that cooling sequence. We can age date the cluster based upon this turn-off information. We can also get lithium abundance measurements and compare lithium versus rotation to see if we can more precisely age date it. And I would love to look at the members that are confirmed as being part of Ursa Major to see whether or not they also have planets, because that would be yet more 400 million year old systems in our backyard. The brightest stars, this is obviously absolute Gaia magnitude, but the brightest stars in terms of apparent magnitude on this plot are a little bit fainter than second magnitude. So there's incredibly bright nearby objects, too bright for Gaia to really give us radio velocities at the brighter and the fainter ends, which is why we need to go in with something like SALT. Okay. And lastly, let's go to moons as worlds. And I want to start by saying, but basically repeating this quote from one of my colleagues, Renee Heller, which is moons are where planets were in the 1990s that were on a brink. And I think that we very oftentimes, when we're talking about exomoons, we're thinking about them as sort of appendages to planets, as not really these interesting objects in their own right. And I will argue that moons are incredibly abundant in our solar system. They outnumber planets 200 to 1. They occupy a wide range in size and mass. This is really because they're sort of determined to be a moon based upon what they're orbiting and not so much their internal properties or their formation processes, which is unfortunate and hopefully will be addressed at some point. But they're also a really hopeful prospect to search for life in our own backyard. And there can be incredible differences in our solar system in terms of the mass ratio. So if we look at this sort of relative scale of Jupiter and Io, my personal favorite moon, and we compare that to the Earth-Moon mass ratio, we're really looking at a factor of 10 to the 4 for this first mass ratio, which is 10 to the 2 times more that than our Earth-Moon companions there. And why is this? This has to do with the fact that there are very different formation mechanisms at work. We believe that the Earth's moon formed from a collision, and is actually part of the Earth that then coalesced. And while we believe that moons occurred much more akin to how planets form versus via this accretion process. And the vast majority, all but our own Earth-Moon system, that we know of in our solar system are much more in this first bucket here. So this is what we're talking about looking for when I'm talking about tempo going forward. Moons in our own solar system are also known to be very interesting places to explore the potential of life. We know that there are these geysers that are emitting from the surface of Europa, which are indicative of this deeper ocean beneath the frozen layer. I'm very excited about the Europa Clipper mission going in to explore this regime. But the idea is that there's actually hydrothermal circulation from tides that's heating up the base of that ocean and is causing this energy basically to propagate through. And this is very akin to possible processes on Earth like chemosynthesis, this idea that you can take carbon dioxide, water, and hydrogen sulfide, and you can end up with sugar and sulfur compounds. So this is akin to photosynthesis, but without the need for photons to catalyze these kinds of relationships. So this idea that you need light for life is actually not very true. You certainly need energy, but you need not have photons to create that energy. And so can there be life on these tidally excited moons, these tidally, these tidally deformed moons? And can you actually have these kinds of life cycles? And do we even have them in our own backyard to actually go look for? What I would really love to do is find moons outside of our own solar system. I'd like to find exomoons that we have the potential to follow up with confirmation, that we can actually do case studies on, that will tell us a lot about those environments. And one way that I've been proposing to do this is to leverage the Nancy Grace Roman Space Telescope, which will launch in shortcoming, but I think has been really sort of lost in the limelight, at least for the major public, because of the exciting and breathtaking images coming from the James Webb Space Telescope. So I'm mostly interested in something known as the Wide Field Instrument, which is the main camera, which is basically going to take images of the sky that have the same spatial resolution as Hubble, this 0.1 arc-second resolution, which anyone who's worked with Kepler attests, that's breathtaking, but will have 100 times the field of view of Hubble. So this is extraordinary. It's going to also have a bandpass that takes you into the infrared. So it's going to be one of the first times that we're going to have this high spatial resolution, time series data if we want it, in the infrared with this large field of view. And it's really the first big data space mission. We're going to be beaming back 1.4 terabytes of data each day. And you can compare that to something like 30 gigabytes with tests to give a sense of how much that is. So I think the potential to do some kind of time domain light curve analysis here is amazing to me, especially when I think about really, really young regions. And I think about some of the filters in Roman. A really young free-floating planet, I'm going to tell you what a free-floating planet is and how prevalent they are in a second, just a planet that has no star at all, floating through space. We see them all over the place. If it is about 3 million years old and 10 Jupiter masses, we have shown you here what its synthetic spectral normalized transmission emission would be as a function of wavelength. And what you can see is that it's nice and bright in some of these filters, the F146 and the F213. By the way, if these numbers sound like made up to you, it's actually just because it's centered on the 1.46 and the 2.13. I remember when I realized that, I was like, oh, duh. But yeah, so there's a hack for you. But to get a sense that these things are just bright on their own. You need not a star's light reflected from them. They're left over formation energy. They are still cooling off. They are bright at 2 microns. This is quite incredible. Wouldn't be incredible if they weren't very prevalent, but they are. And in fact, there are groups like the Cosmic Dance Team that has been looking at, they're calling them isolated planetary mass objects, free-floating planets, rogue planets. They're called all sorts of things, and the community is really arguing about it. They look at planets that don't have stars, that are in these young star forming regions. They take positions, proper motions, multi-wavelength photometry, and they literally count the number of these objects they see, and hundreds of them are being found in various star forming regions. This is an animation of Upper Sco, which is a 10 million year old region. And so we see them also in our own neighborhood backyard here in the Orion Nebula Cluster. And one of the things that we decided to do when Roman put out a request for information proposal, basically asking if you had up to 700 hours of wall clock time, what would you do with it? We thought, oh, we'd definitely go look for these free floating planets to see if they have moons orbiting them. That would be awesome. And we started to simulate that data and to get a sense of what the yields would be. And our first paper, which I implore you if you're interested in this to check out, is the Tempo 1 survey predicting yields of transiting moons, planets, and satellites from the 30-day survey of Orion with Roman. And the second one where I'm really looking for collaborators, this first one talked about the sort of survey design, the main core science goals, and the yields. If you stare at a star forming region for 30 days and you have these short integration times in the infrared, there's lots of science you can do beyond searching for moons around free floating planets. So I'm hoping to connect with lots of scientists that would be interested in leveraging that data for a variety of reasons, to write a paragraph or two about how that might strengthen some of the science cases they care about.
So this term free floating planet suggests that it was once orbiting a star, but is there a way to?
The rogue planet is the one that suggests, because it's gone rogue, but it wasn't rogue. The free floating, I think, is more neutral. Yeah,
So
isolated planetary mass objects, I guess even more neutral than that.
But isn't that just brown dwarf, or is there a real distinction?
Oh, I mean, you're getting down to like one below the mass threshold for deuterium burning. So if you have a 1 Jupiter mass object, it's no longer going to be called a brown dwarf. That's really that 14 Jupiter mass cutoff, because you need a certain amount of deuterium. But these objects are isolated, and there is a little bit of degeneracy though, in terms of if you don't know the age well enough to within 1 million years or so, you might have a slightly more massive but younger object. And so there is some degeneracy in like effective temperature and age that you have to be aware of, which is why they have a range of like 70 to 100 free floating planets.
A similar, right? If they hadn't been around a star at some point, how would they have formed? Is that, okay, sorry,
So
yeah.
I love this question. Exactly. If they hadn't been around the star at one point, how would they have formed? I think that they would have formed as the low mass tail of the IMF, or the initial mass function. And how low does that tail go? We don't know. But if you were to go look for these free floating planets and you were to look at their proper motions, which means you need to come back maybe, a year later, and those proper motions are very distinctly different than the low mass star end or your brown dwarf end. It's telling you about a very different dynamical, maybe ejected history. The moons can also tell you this, because you don't expect moons beyond 12-day periods to have survived ejection. So if you have close orbiting moons, those are fine. But if you had more distant ones, that doesn't make a lot of sense. They would have been unbound by the ejection process itself. So I think the kinematics and the demographics of the moon, of the planets that you find in this way, can tell you about their formation. And what I think is you're going to see some overlap, some that are ejected, because ejection we know happens. These we know that planets can be ingested and they can be ejected outward. But I might expect some overlap as well from the low mass end of the IMF, and I might expect some differences in their kinematics and maybe other things that you can think about in ways that those populations should be different. But at the moment, we don't have good constraints on the low mass end of the IMF below about, I don't know, 0.3, 0.1, maybe there's a better expert in the room, solar masses. And we're trying to go much, much lower than that. And so, what does that tail actually look like? I think we could help to try to understand that. And so that's one component of this Tempo 2 paper, is constraining the low mass end of the IMF. And then trying to also understand formation mechanisms using proper motion studies. It means we can't look at them all in one go, though. We probably need to go back again to see some change. These free floating planets are too faint for even Gaia. So you actually do need infrared, and you will not be able to just use sort of typical Gaia spectral surveys surveys to tell you about the proper motions. Yeah, so if you think of any science cases, extinction mapping, you're interested in transient science, you like, pulsating low mass stars, flares on M dwarfs, dust occultations from, Dipper stars, I would love to collaborate. And, because it's sort of exoplanet tangentially connected science. There's like no real limit on the author list, we just really, let's just write a community paper that convinces the Roman folks to give us some time to stare at a region. And this is what the first region we proposed, which is the Orion Nebula Cluster. This is to give you a sense of the Hubble Space Telescope field of view, if you were to use Hubble instead. And Hubble was used and was toggled many a time in this particular region to count up how many free-floating planets are in that region. And we can extrapolate from that based upon how we expect the density to fall off about how many total free-floating planets can we observe. You may be wondering if Hubble has already looked at these free-floating planets, wonder what the hell do you want to do? It's been done. They've just taken photos of them and they know they're there. They have not monitored them in the time domain for any kinds of transits or any kind of variability. So we, instead of doing this many times, taking lots of photos, can take one snapshot at a time every 18 seconds for 30 days. And we can instead look at the variability signatures of not just those free floating planets, exomoons, but lots of other things. And that is precisely what we want to do. And we have some ideas about what we would expect to find in that field of view, the number of field stars, which is about 5,000, the number of young Orion Nebula Cluster stars, that's between 1 and 3 mega years, is about 2,000, and our extrapolated numbers on the brown dwarfs and the free-floating planets, isolated planetary mass objects, okay, planets without a star, how many, and then what we expect the detections to be, which have pretty wide uncertainties, because there's not a lot known about these young systems. There's also not a lot known about how big these moons or free-floating planets should be, because young systems have very extended hydrogen and helium envelopes. The early Earth is twice as big as it is today. And what does that look like if you were free-floating and you never were photo-evaporated in the first place? Do you have an even more sizable envelope? I'm not sure. So we have a wide range based upon our most pessimistic and optimistic assumptions. We can get a sense of what we would be able to observe just based upon the detectability, just thinking about the 7 sigma signatures that we would try to get. So if we look here at different host masses, planets with satellites and moons, brown dwarfs with satellites and our low mass stars and sort of sun-like stars, and you can see how that changes from host mass in terms of Jupiter masses to the actual Roman magnitude that we would expect for objects at that specific distance. We can get down to Titan-sized objects, and here's where the Earth would exist on this detectable satellite radius. Here's the known exoplanet population, which is again more favorably around sun-like stars, and very little that's known as we go deeper into lower masses. Here is where we would saturate at an absolute limit, even at 3-second integration times, which is how these things are read out on Roman. You get 3-second integrations that you're adding up. So at best, if we're able to keep all of the data, and this is really now about downlink capabilities and onboard processing limits more than anything, we're able to get low mass stars. If instead we think about the 18-second integration, we're really going to be stuck thinking about planets and brown dwarfs. We're going to saturate on everything else larger than that. But what's interesting is that you can get down to Titan-sized companions around these gas giants and around these brown dwarfs, which is quite cool. And depending on the upper limit of the size, if you expect them to be rocky moons, or you expect them to have these extended atmospheres, you may be able to reveal that, but they just may not exist in that form at that point. So this is all sort of interesting and a really important discovery space that I think that we could begin to probe. And so this is basically referring to the point that I just made, that we don't really know what the hydrogen and helium envelopes would look like around these systems. So if we just look at a radius mass relation of our TRAPPIST-1 system and the solar system and compare that to models of rocky satellites with known exoplanets, and then objects that are immersed in disks at different times, what you can see is that the satellite radius changes substantially. With Earth is about 2 times smaller today than it was at its earliest time, or at least at 1 million years. And so this is something to be aware of, that there's those uncertainties, but then there's also the potential of that discovery. And so something else that we're doing is actually synthesizing the data. We're creating synthetic data to try to understand, based upon the occurrence rates that we know and a lot of uncertainties, what do we expect the sort of mass companion separation discovery space to be of masses that are free-floating planets, our brown dwarfs, and our stars. And assuming we can get down to sort of, sorry, not assuming, we're able to get down to objects for reference that are going to be, Io mass size and Io orbital separation. Europa, Ganymede, Callisto are shown here. Here's where your Earth orbital separation would be. And then our synthetic results are shown here. Again, depending on how you saturate and whether or not we're able to get back intermediary reads. But if we're able to get the lowest mass stars, we can get these sort of early proto-habitable Trappist one-like systems. We certainly can probe companions around brown dwarfs and companions around these planetary mass objects or free-floating planets. And this is the sort of expected ensemble of objects that we would expect to find. So we have the different circles representing different sizes. So I think it's an exciting discovery space and one that even if you have the most pessimistic of yields, would still reveal a lot scientifically. Okay, I talked a little bit about all the science you can unveil. We even had someone in the audience already guess that there might be some interesting formation mechanisms like constraining the IMF. Here's just a few of them that I think Tempo would have the capacity to be able to touch on, and I'm excited to hear more if you have them. I'm particularly interested in that low mass end of the IMF conversation, and if you have any insights on that or want to think about other ways to probe that, please do let me know. And I'm going to end it here, but just letting you know, I've talked about the analysis of planetary engulfment signatures. I've talked a little bit about Ursa Major with SALT and wanting to look for more systems. I've talked about young planet characterization and detection. I've certainly talked about Tempo, but I do have another project that if you have time and interest, I'm really interested in the classification and also like deeper scientific inquiry on variable stars and open clusters. And I'm currently looking at original Kepler data of NGC 6791 and 6819 to try to understand what sort of variables are therein. I'm particularly interested in like the blue straggler pulsators. So if you want to talk about any of that, let me know. And these are some of the amazing students that really like, make this all happen and make this also a joy to do. And with that, thank you for your time. This has been great.
Thanks very much, Melinda. Questions from the audience?
Yes, so how common are these like free floating planets are there compared to like normal planets? Because I heard somewhere like rogue planet, there are like much more of them than a planet. So, like what about the free floating?
Okay, so I think right now we're grouping everything in one category just because so little is known about the proper motions. And you're right about there being an overabundance beyond like what the models anticipate. It's also true because you have these young stellar populations. At 1 billion years old, these stars have not converged onto the main sequence. They're super extended, very luminous, really difficult to monitor for transits. Really amenable to astroseismology though, and we should talk about that offline. But it means you don't have a sense of the bound planet population to compare to. And so really, anytime you're hearing free floating planet, rogue planet, isolated planetary mass object, I think people are using these terms interchangeably because there's just such a small census demographic right now. When we have proper motions, I think we'll be able to classify them better. But what I would love to do beyond even proper motions is classify things by their formation and internal structure. Like the physics would be interesting, but I think that's going to be many IAU conversations from now.
What like timescales when you have that like planet in spiral and you get like the flare, like what time scale is that happening on?
That's a good question. We know once that you are being ram pressure stripped by the stellar envelope in any way, it's a few integer orbits. So that really depends now on the orbital separation and that, basically what your period is. But the in spiral, the tidal loss over a function of time that may be happening at a much more distant separation, that's harder to tell. There is some interesting work with like WASP-12b and looking at its period change as a function of time and then being able to extrapolate from that period change. And that's on the order of a few million years. So you can go that far out, but once you sort of starting to touch and graze the star, it's pretty quick, is what we're seeing.
Brian, it's all you.
Oh, thanks, Melinda. So you mentioned that you were looking to see if there were elements other than lithium that were peculiar in the when you had suspicions of engulfment. So what other elements did you find?
I don't know how much, I'm nervous about how much to share, then somebody goes out, but you guys are a good crowd, right? I will tell you that there are 30 other lines that we're seeing. There are 2 tracers in particular that are lithophile species, so up there in sort of the, not the atmosphales, but the next layer, that are
Yeah.
showing up in with strong statistically significant absorption features. But really, it's the whole row from scandium out to copper. We're seeing little hints of things there, which makes sense because if gravitational settling is occurring, things like, for example, thorium, I would not expect to find in that sort of, being radiatively levitated or something. But we really are seeing sort of a wide range, but there's a couple tracers in particular where there's an ensemble of lines in a way that's really quite compelling.
Oh, that's super cool. Thanks.
Yeah.
This is maybe kind of a naive question, but when we're talking about you're stripping off sort of the atmosphere first, what is the time scale for you to actually get down to these like lithophile tracers that you're seeing?
Yeah. I don't know that I have a sense of intuition about this. I know the things that you need to account for are the planet's going to puff up as it's getting closer. We see this sort of puffing up and enhancement. The tidal dissemination of the planet is actually usually interior to the star, so you're already engulfed by the time that's happening. But once that's happening, that's really taking over the unbinding process. There's also a ram force that's just sort of facing this density gradient of wind that is going to unbind the material. There's a beautiful paper by Gia and Spruitt from 2018 that looks at how you unbind based upon the ram force. All of these things are happening simultaneously, and then on top of this, at some point you release enough of that overburden pressure that it's even helping your case. But I don't have a sense yet of what, like, intuitively that time scale will look like for, I don't know, for like our system of interest, for instance.
This one's for me, not from the computer.
Sorry, Tony, I should let you pick the.
Oh, sorry.
Go ahead.
My mom energy is just.
So, has there ever been like an observed instance of a star expanding, absorbing something that destroyed it before it?
Like forming a ring or something?
Yeah,
you
like,
mean?
so if a star ever absorbed something that was so considerable, like of a considerable size, that would like cancel or noticeably interrupt its death.
I mean, does it have to expand? I'm thinking about white dwarf planets and white dwarf accretion, because the white dwarf is so much denser. We definitely see this sort of tidal ensemble, and 50%, 30 to 50% of all white dwarfs have pollution signatures in their atmospheres, and we're seeing them creating this sort of ring of debris. So white dwarf accretion is also very, very interesting. And you see it in real time because the timescales for a white dwarf's material to settle, it depends on whether it's hydrogen or helium dominated, but it can be weeks. So if you see anything, something's happening now. And there's even signs of like soft X-rays that are showing what the accretion rate onto the surface is. And so there's an exciting proposal that somebody just got accepted to look at that in Chandra in real time, to look at it in time and see how that accretion rate changes as a function of time. But for the expansion and all of the things that you're talking about for thinking about a star, it's the only one that we know of in real time that we've sort of seen this sort of event is this very distant Nature paper star, which we saw just an optical object emerge, but only after we went back and looked for it because this weird infrared signature was doing something unexpected. So it would be really wonderful to happen in our backyard and we could kind of see, more spatially resolved information.
Maybe along the lines of your question, Spencer, there has been this idea that blue stragglers are kind of rejuvenated by accretion, and so they're able to extend their lifetime somehow. Is that still considered a leading explanation?
That is still considered, I guess it is extending their lifetime, because they're appearing on the main sequence but should have turned off. You're accreting this material. If you merge, you entropy sort, and are sort of, the reason I'm thinking about it not being so rejuvenated is because you're adding it to the outer part of the star, but is it really hitting to the core to like burn core hydrogen in a different way? Or is it just sort of appearing as if it's more massive and it's, I don't know, whether or not the luminosity and the mean molecular weight and opacity has changed versus it's really burning hydrogen in a different way? I'm not sure. But certainly it appears on a CMD that you would age date to be rejuvenated based upon that interaction. If they do merge though, you even get entropy sorting, and you really do have a rejuvenated star in a much deeper way where I think the interior structure is much more similar to a star that had been born with its M plus delta M merger product. Yeah. I really want to do astroseismology on blue stragglers because then you can start to probe the internal structure, the rotational profile, and see where the angular momentum is deposited as you sort of move through. You can also get a mass estimate about that. You can compare that mass to the main sequence turnoff mass and get a sense of what sort of progenitor was there. I think you can constrain it a lot more. And the beautiful thing about blue stragglers is they're in clusters. That's where the constraints are the best. And so it's not that they're just in clusters, it's just that's how we see them and know them and love them. Yeah.
Any other questions? Yes.
How common is it for the lithium abandonment or sort of the tracers of transient to be present due to an spiraling planet rather than just any other reason such as like beryllium decay, as you mentioned?
This is a great question. I would say there are parts of the HR diagram where to get the kind of lithium signature that you're seeing, a planet, you'd have to supply thousands of planets to do that. Something like the red clump, for instance, which is where giant stars tend to linger for a while just due to their evolutionary history. Most certainly, there's beryllium is decaying into lithium, and we know that there's all this mixing processes going on. Beryllium decays really quickly, decays in like 56 days. So you need to bring it up from the depths of where it was created via the PP chain to that surface fast. That can happen for those stars. For stars in the region that we're interested in, it's uncertain, but what I can tell you is that 1% of all evolved stars are lithium enriched. But unless we have other tracers and other ways of really knowing that that enrichment is not due to some intrinsic process, or maybe even a novae nearby, novae produce lithium-7, and you're just preferentially near one, I think unless we can get an ensemble of tracers that really point to a substellar companion, there's some ambiguity there, but certainly they're common if you think 1% is common, which I with the astronomical numbers, that's a lot of targets, so common.
Okay. Yes.
Adding on to his question, how do we know that that lithium is actually coming from planets? Could it not be from other sources, like maybe just asteroids or past experiences of the star, which we don't know?
Oh, so another substellar object. I think the amount of lithium, right? So the lithium that I'm inferring based upon the excess absorption from the object I showed you is inferring a five Jupiter masses worth of lithium. So you'd have to rain hellfire of asteroids for that to happen.
Exactly.
So that I think you need a significant amount of mass. What I would love to do is to take another tracer and determine if that mass agrees with what I'm inferring by lithium, because if we know lithium can be formed in these other ways, how much of it is because of a novae or because of the self-enrichment? So imagine I have a secondary tracer that doesn't have that degenerate pathway. I think now not only can you get a sense of whether your mass is right, but you can also get a sense of what sort of preferential, is there extra mixing that's going on in the star? Was there a novae there? And I think it tells you other clues about other physical processes. Yeah, but it's tricky, yeah.
All right, we should wrap things up,
Okay.
but thanks everyone, and thanks Melinda for.
Thank you.